Hello, Internet. Welcome to episode 61 of the Stanford MLSys seminar series. My name is Dan. Today I have with me Fyodor,
Hello.
Piero,
Hello.
Karan,
Hey.
and our guest Cushion.
Hey.
Today we'll be discussing some of Cushion's research on big data analytics. We're very excited about that. A little bit about Cushion before we get started. Cushion was a PhD student here at Stanford before she graduated. Now she's a postdoc at the VMware Research Group. In the summer, she's going to be starting as a professor at Georgia Tech. So we're very excited to hear from her. And with that, Cushion, take it away.
Thanks for the introduction, Dan, and thanks for having me. So today I'm going to take the chance to tell you guys about some of my work on combining learning with indexing and sampling designs to improve query performance in big data analytics. So I'm sure that you have heard this from many people many times, that we're seeing a lot of data because there are more sources that are collecting data, also because the storage costs are decreased due to big data systems such as Amazon S3. So to store and process these large volume of data, many modern analytic systems now store and process these data sets using data partitions as a basic unit for storage. So systems like Snowflake, Spark, and Hive. So what does data partitions mean? So partitioning is basically a way to split a large table into several smaller parts. So each partition basically contains a large number of rows, usually thousands, tens of thousands to millions of rows. And because these are large chunks of rows, they can be efficiently compressed, usually using a columnar format. And then each of the partition end up getting stored as an individual file on disk or cloud. So you can think of a partition as a parquet file on S3, for example. So the question is that what does it mean for data analytic systems who want to process SQL query efficiently on these data partitions? So before, we had traditional databases that operate on individual rows on the table. So what happens when we use partitions instead? So let's look at two classic ideas in database systems to improve query efficiency, namely sampling and indexing, and see how this change from rows to partitions will introduce some interesting questions, starting from sampling. But before, for applications such as data exploration, where you might want to approximate an answer to a SQL query, one way to do it is to select a subset of the rows from the table and then compute the answer to the query using these rows. And there are many related work that focus on how to select rows to better do this approximation. But now the problem is that constructing this row level sample is becoming a lot more expensive in this new setting. Recall that each partition is basically a compressed file, and there isn't really easy access to individual rows. So here, if we want to sample one row, you need to read the entire partition. And to do a basic back of the envelope calculation, suppose each partition just have 100 rows. If you take a 1% row level sample, you read 60% of the partition. If you take a 10% sample, you need to read almost all partitions. So this is pretty bad news for sampling because it diminishes the I/O gains. So since sampling on the row level is expensive, the natural question is that, can we sample on the partition level instead? And by partition level, I mean that you either read all or none of the rows in a partition. And unlike row level sampling, if you actually take like a 10% partition level sample, you only need to read 10% of the data. So the new problem is that, given data set and the query, how do I select the best partitions to try to minimize the approximation error to SQL queries? So that's the story on the sampling side. And now let's look at what happens for indexing. Okay, so in traditional databases, you have these indices such as B trees that can help you locate rows quickly. So for example, if I want to run the SQL query that try to compute the sum based on records whose metric equal to 5, I can look through this index, which will eventually lead me to a number of row IDs. So I can look up these rows quickly without scanning large parts of the table. And now that data is stored and processed as partitions, it doesn't make sense to optimize for these low row level information. So what we have instead is a much coarser level partition level metadata, which can think of as a coarse-grained index on the partitions. So for example, here for each partition, we can compute the min and max of the values for each column and use information like this as an index information. And this can also help us run queries efficiently. So taking the same SQL query as an example, here, before running this query, we can check this predicate against this min max of each column. And in this case, only partition 2 can contain values that possibly match this predicate. So to answer this query, we only need to read partition 2, but we can skip partition 1 and 3. Compared to if you read process another SQL query that queries on the host column, unfortunately now all the partitions contain relevant information, so we need to read all 3 partitions to answer the query. So as you can see here, the way you actually divide the table into partitions directly affects how many rows will be read to answer your SQL queries, therefore the query performance. So now the question is that how do we design these mapping functions that assign individual rows to partitions so that we can read as little data as possible to process our queries? So this is the indexing story. And these two questions are basically what we're going to cover for the rest of this talk. And specifically, I'm going to talk about how we can combine learning techniques to better design these indexing and sampling to make them work with data partitions. And we'll first start with sampling, and I will talk about PS3, which is a system that enables weighted partition level sampling. And our evaluation shows that it reduces the number of data you need to read by 3 to 70x compared to randomly selecting partitions. And then for the second part, I'm going to talk about an online learning framework for data organization. So we can organize data according to changes in the query workload. And we show that using this dynamic organization results in up to 30% faster query time than using a single static layout route. So without further ado, I'll jump into the first part of the talk, which is collaboration with Yao and Shrikant at Microsoft and my PhD advisors, Peter Bayless and Phil Levis. And this work is published in VLPB 2020. So recall that row level sampling is expensive in this new setting. So we want to sample on the partition level instead. And in fact, because this partition level sampling has good performance, uniformly select partitions as samples as a functionality is already supported by many commercial databases, such as Oracle Postgres and Snowflake. However, the problem is that randomly uniformly selecting partitions can lead to large errors in the estimate because rows in the partition can be correlated. So in this example, our table is divided into 100 partitions with according to the categorical column X, and 99% of the partitions contain M as a value for X, and 1% contains SAM for the column. And we want to answer the query, select the sum of Y grouped by X. And here, if you randomly select partitions to answer this query, it's clear that you're not very likely to see any rows for the SPAM group, which exists in one of the 100 partitions. And we know that from experience working with row-level samples, that having stratified or importance type of sampling can be important for query accuracy, especially for more complex queries with group bias and aggregates. But it is not known how to do this on a partition level. So this is the problem that we're trying to address in this work. So specifically, we're given a partitioning of the data set, and we do not try to change this partitioning throughout. And we have a sampling budget in the form of how many partitions are we allowed to read and then target query from some workload. And we support queries with sum and constar like aggregates, arbitrary predicates, group bys, group with median cardinality. And for the workload, we assume that we know the group by and aggregate functions in the workload. And for the output of the system, we want to output a selected set of partitions and its corresponding weight. So for example, here our system decides that we want to read partition 1 and 100. So we only read these two partitions and evaluate the query on them to get some partial answers. And combined with the weight assigned to the answers, we'll have a final estimate for this query. And the goal is to select partitions and weights so that the error for the estimate is as small as possible. And in this example, this estimate has a 1% relative error in estimating the aggregates for the ham group. And our solution PS3 stands for partition selection with summary statistics, which focuses on read-only and append-only data stores. And the key idea is essentially that we can pre-compute a bunch of lightweight summary statistics offline as features for each partition, and use these pre-computed features to help us make better decisions on how to select partitions online. And the result of the prototype shows that we can reduce the number of data read between 3 to 70x to achieve the same error compared to randomly selecting partitions, and that the per partition storage overhead is relatively small, like less than 100 kilobytes. So now let's look at how the system works in a bit more detail. So PS3 contains two main components, the stats builder and the partition picker. So in the offline phase, the stats builder takes as input some raw data partitions, and then it outputs a set of summary statistics for each partition. And in this phase, we only compute simple single column statistics such as range of each column. And then in the online phase, the stats builder additionally computes some query specific statistics such as selectivity to append to this feature vector. And combined with the query and the budget, the picker is then able to select, produce this weighted list of partition selection, and this entire process happens during query optimization. So that's how the system works on a high level. And let's look at how these two components work in a little bit more detail, starting with the stats builder. As I have hinted before, existing system already stores some lightweight stats such as min and max for each partition as metadata information. So our idea is basically to expand and build on these existing statistics stored to have them contain richer features that we can do more with it. So specifically, we propose to use a set of sketches, histogram, measures, distinct value, heavy hitter, and each of these sketches will allow us to compute some summary statistics for the partition. So for example, measures give you moment, histogram gives you selectivity, distinct values give you distinct values. And I also want to mention that these statistics vary slightly from query to query. So although we always compute the stats with the same schema for each partition, the actual numbers might change from query to query. So given these list of feature vectors, the question is then, how does the picker use it to actually improve the partition selection? So here we have two ideas. And first is that if we knew which partitions contribute more to the query, then we could improve the quality by sampling the more important ones more frequently. And the observation is that these summary statistics as feature vectors does provide information in helping us judge or distinguish which ones contribute more to the query. So for example, to answer this SQL query well, we might want to select partitions that have large values in Y, have many distinct values in X to answer the group by, and many rows that satisfy the predicate to answer the where clause. And for each of these desired criteria for selecting partitions, we can find some corresponding summary statistics that provide evidence, right? But the problem is that it is hard to manually qualify how does each summary statistics relate to the partition importance. So guess what? What we did is to formulate it as a learning problem. So instead of manually building the rules, we try to train models that take as input these feature vectors for each partition, and then as outputs, classify them into a few groups of varying importance. So a bunch of classifiers, that can basically group these partitions, and then we're able to assign basically different sampling rates across these different importance groups, so that we assign more sampling budget to the more important group and less sampling budget for the less important group. And I'd be happy to chat more about why we chose this specific learning problem formulation in a Q&A, but just for now, I would just say that we do this training for each query workload, and we only consider generalization to unseen queries in the workload, but we do not consider generalizing to unseen data layouts or data sets. So that's the first idea of trying to leverage the partition contribution to help select better samples. And the second idea is to leverage the redundancy of the existing partitions. So the idea is basically that if you have two partitions that contribute similarly to a query, maybe you only want to include one of them in a sample. And again, we use these summary statistics as feature vectors, and we use class strings to try to choose dissimilar partitions as representative samples. So for each cluster, we select one partition as an example, and the weight of the partition is essentially the size of the cluster. So that's kind of how this redundancy idea works. And I'll defer more details to the paper, but for now, I'll jump straight into evaluation and see whether this approach actually works. So first we run an experiment comparing query accuracy. And here we compare against 3 baselines. First is randomly selecting a partition. The second is the random partition selection plus some predicate filter. And the third is the prior work that tries to learn to generate stratified samples, but we modify this to work with partition level instead. And for the results, we report on the TBCH dataset with a scale factor of 1,000. The paper experimented with more setups and datasets. So for the query, we sample workload that consists of randomly generated queries that look like the following. They have some aggregates, predicates, and group bys, and we use some of the workflow for training and some for testing. And for all methods of comparison, we compare the y-axis is the relative error achieved by method, and the x-axis is the percent of data read by different methods. And in particular, this x-axis is a good proxy of the total compute hour you need to spend on evaluating these queries. And here are the results on the four methods that we compared against, with PS3 as the bottom blue line. And in this particular example, it with only 1% of the partitions read, it is able to achieve a 1.5% relative error in the estimate compared to the other baselines. The modified stratified sampling needs to read 5% of the partitions. And if you randomly select a partition, you will need to read 70% of the partitions to get the same error. So 70x faster in this case. And in terms of the overhead of the system, the storage overhead for the sketches and the summary statistics ranges from around 12 to 100 kilobytes per partition. And this is essentially a constant and small compared to the partition sizes that are often in the megabytes and gigabytes. And this single thread latency of running the picking logic, which includes, the classification and clustering, ranges around 100 to 1,000 milliseconds, which is also small compared to query time and can be further improved with optimizations. And we show in the paper that the framework work under different number of partition counts, different layouts for different query selectivities. And even if we did not train the models on TBCH queries, it can still evaluate, generalize to unseen TBCH queries in the evaluation. So some reasonable levels of generalization to unseen queries. So with that, I will stop for the first part of the talk, which is about how to better collect, better construct partition level samples. And our system PS3 is first of its kind to try to construct a weighted partition level sample and have reasonable generalization and improve significantly compared to uniformly sampling the things. Okay, so with that, let me go on to the second part of the talk, which is about indexing and how to organize the data. And this is ongoing work on collaboration with Paul Liu and Moses Charikar that we're still submitting. And recall that in the intro, we discussed that there are many ways to partition a data set. And the way that you actually map these individual rows to partitions have a direct impact on query performance. So the natural question is that, how do I design this mapping function to row IDs, to partition IDs, to maximize the skipping capability? So luckily, some smart people have already looked at this problem. And what they've realized is that if you design these mapping functions, these layouts that specialize the design to specific query workloads, you can achieve very good performance. So for example, this recent paper proposes a data structure that essentially, extracts predicates from your query workload and use these predicates as part of, the index construction. And by really doing this specialization, they achieve the best performance in, how many partitions they can skip for a given workload. But, as you can imagine, if you really specialize a design to some target workload, similar to overfitting problem in ML, if the target workload shifts, your design will also experience significant performance degradation, right? So what should we do? What should the data analytic systems do when the target workload changes? There are essentially two options. One is that you can change your design to try to adapt to the new changes. And the other is to do nothing. And when the cost of switching is relatively low, it is indeed beneficial for you to change your layout to adjust for the changes, because eventually the gains in your query cost will outweigh the reorganization cost. Versus if your cost of switching is high, and or if the new workload pattern does not last sufficiently long, then you might be better off, staying in your current design, because at least you do not waste paying this reorganization cost. So during query processing, the analytic system will constantly face this question of should I change my design, or when should I change my design? What design do I change it to? And at the end of the day, end users for the system pays for resources that are used both for query processing and for reorganization. So as designers for the systems, it makes sense for us to optimize for the sum of both costs instead of only focusing on, for example, reducing query costs. So the question is basically, for unknown sequence of query that the system is seeing, can we make smart decisions and on when and how we should reorganize the underlying data so that we can minimize these total costs on the system over time. So one approach to solving this problem is to model this as a learning task or a prediction task. So you can imagine that, if we use supervised learning, we can try to predict what future query workload will behave and then make decisions based on that. Or, without explicit labels, you can also use things like reinforcement learning to try to model the reward of different actions. The baseline is that you depend the decisions on the organizations on this predictions of the future. So there are some work that, try to do some of these prediction tasks for, slightly different, but also like tuning tasks in databases. But in this work, or in our case, we take a different approach and explore the online extreme in the design spectrum. So we specifically, we chose to use online algorithms, which assume no prior knowledge of the query workload. And it also does not rely, it does not rely the decision on the prediction of the future. And using online algorithms also have the benefit of providing the worst case performance guarantees in the form of competitive ratio, which is, the cost of online algorithm, which does not know the query sequence divided by the cost of an offline algorithm, which observe the entire query sequence beforehand. And classic online algorithms tell us that if we're given a state space, say state space containing 3 different possible layouts that we can switch between for the decision making, then we can get a competitive ratio that's on the order of log of the size of the state space. Okay, so are we done here? Should we just apply online algorithms to our problem and call it a day? Unfortunately, in our setup, one challenge comes from the size of the state space. So recall that our state space is basically this mapping function between row ID to partition ID. So it will be intractable for us to try to enumerate all possible partitionings in this space. And because we also don't know what workload is coming, we cannot pre-compute this state space. So what we could do or would like to do is to start maybe with a default organization, and as we observe more queries, add and remove different organization or different layouts to the state space over time. But this requires these state space to change over time, versus in classic setup for online algorithms, you work with a fixed state space for the entire query sequence. So that's kind of the main technical challenge in this work, how to adapt traditional online algorithms to work with a state space that can change over time. And basically, we show that we can modify the setup to do this and can achieve a competitive ratio that's on the order of log of the maximum size of the state space. So here's a high-level overview of the solution that we built. For input query sequence, we want to generate this reorganization decisions, and our framework for online reorganization contains 2 components. In the first component, the layout manager just observes new queries and then try to issue update, try to add and remove states from this space. And then the reorganizer just consumes the space, the available layouts from the state space to make these decisions using online algorithms. So that's kind of how it works on a high level. And again, let me jump straight into evaluations and show you how well this works. And for this evaluation, we compare the end-to-end time for both query and reorganization using a standalone Spark setting. And for the methods, the static baseline is basically the best single layout you can build for the entire query if you know it in advance. Periodic is, periodically you evaluate whether you should build a new layout, and if it's better, you switch to it. And regret is that you keep track of the cumulative regret or performance difference between your current layout and alternatives, and switch to alternatives if the regret is larger than movement cost. And then again, on the TPCH data set, and then for the workflow, we include 37 queries generated from 20 templates. And to simulate workflow change, what we did is that we streamed queries from one template for an arbitrary amount of time and then switched to another arbitrary template. And we measure query and reorganization time. And here's the result. And compared to using one static layout throughout, in this case, the dynamic reorganization improves the total computation time by up to 30%. Without knowing the query workload in advance. And I'd also want to mention that this framework is agnostic to how you actually generate the layout. So it can also work for other, simpler layout generation mechanisms such as Z-order. Although the performance is a little worse on the Z-order because, it generates slightly worse data layouts than QD tree. Okay, so I will also stop here for the second part of my talk. And before I open up to Q&A, here is one interesting little question to think about. So I talked about sampling and skipping in this talk, but you might have realized that they actually require very different organizations for best performance. So if you're doing sampling, you want all your data to look uniform. So you only need to read one thing and then get a representative sample of the whole data set. Versus if you're skipping, you want everything to look as different as possible, because then if you issue one query, you only need to touch a few partitions. So how do you actually combine both contradicting designs in one system? Will be an interesting question to think about. Okay, so with that, I'd like to stop here and I'm happy to answer any questions.
Thank you so much for that talk, Cushion. It was really great, and we definitely learned a lot. As a reminder to the audience, we're about to transition into the public Q&A portion. So to anybody in the YouTube audience watching, feel free to send in those questions in the YouTube chat, and I'll summarize them and get them to Cushion. So I'll just get us started with a question. So coming kind of from a ML or MLSys side, one of the things that I noticed about the sampling ideas that you're talking about kind of like sampling based on the summary statistics or clustering, seem like they could potentially be applicable to more complex data like images or natural language as well. Like you can imagine maybe applying this to data selection for training machine learning models. Have you thought about kind of taking the ideas that you have in this space and trying to apply them to a machine learning setting or anything along that vein?
Right. I think that's a great question, and yeah, in a lot of ways, the approach, both the approach that we took can be summarized as right now manually crafting some feature vectors for individual objects, and then learn classifier to try to learn some objective, right? And then this overall paradigm, obviously, as you suggested, apply to many other types of data other than tabular data. So I think that I guess there are two questions to think about, right? Like one is that for this particular work that we did, I was the domain expert who designed this, right? And then I imagine for many other domains, right, the default is to also design these summaries, right? But I think for it to be fully automatic and generalizable, it will be great to have a more automatic, feature generation and selection metric to cover that part, right? And then it will become like a, some automatic, feature generalization for, tabular data and other type of data, and then obviously which type of features you generate also relates to the downstream task. But yeah, I think there is a lot of potential. And one interesting question would be to summarize the commonalities and difference between these use cases and see which part can be automated and which part still needs domain input. Yeah.
Right. I wonder, in that process of designing those features with your domain expertise, were there certain features that you found were particularly useful, maybe across different data types? Is there any of that maybe secret sauce or knowledge that you could maybe tell us that would be broadly applicable? Any of those lessons that you learned in that process?
Right. So actually, the single most useful, I think, criteria for how we design the feature are like the cost, right? So because we're storing these additional things for partition, and then we're also computing these features potentially repeatedly for different partitions. So cost is obviously one very important aspect. And as you can see, like some of the features that we crafted and stored are not super advanced, right? It can be as simple as sum or like min and max or some simple statistics, that gives an overview of the data. So, but the reason why they're in there is one important reason is that they're cheap, right? And then to compensate for the information, because these are very cheap features, we try to compensate it by having a diverse set, having many different sources that can produce a large set of these cheap features. So that's kind of our overall design thought or philosophies in trying to come up with this thing. So in the sense that instead of training a large model to give a very good embedding, we took the other approach of throwing a lot of cheap and easy to compute things and just try to collect different information. Yeah.
Gotcha. Thanks so much.
One thing I can add on this, which is interesting to me, is I don't know if you're familiar with this set of models, but that whole task, the sampling task, and some of the solutions remind me a lot of core sets.
Yeah.
And again, if you're familiar with that, I'm curious if you can, like, if you also thought about that, the connection, if there's anything there that you believe it's worth exploring, or what's your take there?
Right. Yeah. So it's definitely very related to core set. From my understanding, it's also you try to build a representative subset of the data, right, for some specific task. And I think that what we are trying to do is, and a lot of I guess existing solutions on how to do this on the row level also relates to ideas for building core sets. So I guess I don't know the specific core set literature that well, but from my understanding, there is also some you can build different core sets for different like target metric or applications, right? Like for kernel density, it's like one core set. For some other application, it's like another core set. So and SQL query is just like one other type of end application. You can think of, we're trying to build a core set, but then our end application is SQL query. And SQL query, in my opinion, is not a very simple end application because it can be very complex. You have all these different components of computing different sums and having the filters and group bys and all that. So I think on a very high level, this is essentially building a core set, except for a slightly different end application. And unfortunately, I don't know too much about the specific techniques on how to build core sets to comment on the relation, but it is like very similar questions on this like intuition level.
Yeah, that's great. And actually, this also triggers another question that I was thinking about, which is you showed that one example of those queries. How do they look like from the data set? I'm curious of the variety because obviously the bigger variety in those data sets, the more representative those results will be of something that is generalizable, right? So can you give us like just a little bit of an understanding of the variety of the queries within those data sets?
Right. Okay, sounds good. So how we, what kind of query workload do we target? And how do you generate these like training and testing workloads? Yeah. So I think what we did is basically have, the basic query template is, select some aggregates from a table where some arbitrary combination of predicates and group by some one or more columns, right? And then for each of the fields, there are some parameters you can fill in, right? So for group by, there are like specific columns, usually categorical columns that you can input it in. For like the aggregates, there are like some on different columns or different like algebraic information that, it's basically like different aggregate functions on different columns. And then for predicate, actually, we do not have any restriction on predicate. So it can be any predicate, like range query, point query, queries with like and or clauses. So that's kind of the space, and how we try to generate a repetitive sample is to, have this template and then just try to sample, randomly combine all these parameters for this different place, and that's our query workload. And this is why the generalization experiment to TBCH query is interesting, because we did not specifically train on the, so TBCH is like a subset of basically the templates that I described, right? So we did not specifically trained on actual TBCH queries, but we trained on queries that, belong to the larger space that could generate the TBCH queries. So what we did is basically see that if we train on this larger space, which, contain these randomly generated queries, do they work on TBCH queries? And the result that we got is that, yes, it generalized to some extent. It like it still improves upon random, even we did not explicitly train on these TBCH queries. And I hope that helps.
Yeah, thank you very much for explaining this. This makes a lot of sense. And again, it's interesting to have old out templates to begin with, right? Because otherwise, yeah, so this makes a lot of sense to me. So thank you very much for your answer.
Hey, Kexin, I was just curious about, I guess, handling kind of data that's maybe rarer, especially, data that might not have, enough samples, and you have to maybe look at a particular partition to actually get information about it. So I guess a couple of concrete questions there. One was just, in terms of relative error that you saw, did you see that like that relative error is kind of distributed kind of non-uniformly on the types of queries that you're receiving, like maybe queries that actually hit these like more rare categories, for example, in your data could be penalized through this approach? And then I guess just more generally, I was wondering in terms of the features that you designed, one of the things that struck me was like, what is the relationship of the partitions distribution of data to the global distribution across all partitions? And I was just wondering if you could comment on whether you had features that kind of captured that relationship, like, for example, kind of divergences between global and local distributions of data.
Right. Okay, thanks for the question. So I'll comment on basically the outliers first. So I think outliers definitely account for, large errors, especially, like in the examples that I gave, right? You could do very well on one group, but like you will have like 100% error on the other group. So actually in the actual system, we do have some dedicated budgets for outlier distributions. And I think I forgot how exactly we select outliers, but I remember we basically have like a small percent of our budget that specifically targets outlier like partitions, and that help with the error a bit for sure. And then in terms of the error metric that we use, so we basically check all kinds of error metric, right? We check not at relative error for one group, but we try to average it across multiple groups. And if you do relative error, then it accounts for the difference in like relative absolute value, right? So it's more fair to look at it across groups. So I think it's definitely hard to address outliers, which is why we allocate a separate thing for it. And ideally, like I think like for any systems, like that's usually the way to go. You either like include the outliers in your evaluation, or you like have a way to pick them out, and that will help with like a lot of the corner cases. And then for the other question on sorry, I forgot. It's relating to the global and local summary statistics. Yes. So I think that's a very good question, and we did not. I think we did not explicitly model the interaction between local and global. I think our attempt was through this clustering, right? It's like we try to see which other partition might relate to this partition, but and then that's our like global view of how these relate to each other. And actually, that was like a big help, because there are some things that actually look surprisingly similar to each other, right? And then it helps a lot if you like know that they look similar. But I guess we did not explicitly, compare a global feature and then look at, how it differs from the individual features. So the global part was in this case handled via like the clustering type of approach.
The redundancy between clusters, basically. Yeah, that makes a lot of I echoing what Dan said, I would be very kind of curious to see, kind of the like moving from feature engineering to learn everything kind of approach, and that will be pretty exciting as well, I think.
Right. Yeah. I think that will definitely be, more automation is always the direction, right? For this work is more, I would say, proof of concept, because, we had this intuition that these feature vectors, these summary statistics can relate to what we care about. And, this is basically attempt to prove that the correlation exists, right? Yeah. But then, I think eventually, if the more we can automate, the better, for sure.
Yeah, there's definitely signal.
Hey, Kexin, in the second half of your talk, it was kind of based in this setting where you have incoming data streams, right? Where distributions might change. I was curious if you could talk about that setting and how the first half of your talk on picking partitions, does it become more challenging, and how, if you try to kind of extend this partition picking problem to a setting where data is coming in kind of frequently and distributions might change some arbitrary frequency?
Right. Sounds good. So I think so for the first one, there is a part that depends on the workflow, which is that we train the classifier to classify the partition into different groups based on some workflow, right? So if the income query shifts significantly, you will need to retrain the classifier to update the grouping. But otherwise, like the other part of the structure does not need to change. So basically the difference between, I guess, the first half and the second half is that first half, like we never change how the data is organized. We assume that, they always stay in this partitioning that is given. So what we are changing is which things, which samples we pick for which queries. And then, so the picker, how we classify things can change according to query distribution, but we do not need to, change how the underlying data is structured. Versus in the second part, we're trying to look at, okay, how do we change the underlying data organization to adapt to workflow changes? So that's kind of how I imagine, the picking will work for changing query workflow.
Got it. And how much effort is it to kind of retrain your partitioning if the data changes?
Right. It's I think it's not. So the main thing is that the features do not change that much, right? So because we for each partition we always compute the same set of summary statistics for each column, so it's like the same schema, right? And it's like same effort to generate everything. I think it's just like I think the training itself will not be that difficult, but you need to collect some labels before training. And the labels we use for training, how do we classify is basically we need to evaluate queries on the partitions. So our ground truth is basically how much does this partition actually contribute to the query answer, right? And then based on that ground truth, then we can train a classifier on that. So to retrain, we will need more examples on, how much does each partition contribute to the new query workload, but we can collect those if we evaluate the query on those partitions, right? So once if you just run the query on the partition, you will know what's the result. So I would say it's definitely some work, but not terrible. And you can collect more signals along the way. Yeah.
Yeah, it makes sense. I mean, the interesting thing about these big data sets is that as data is coming in, the actual distribution of the data changes gradually just because there's so much of it typically to start with. And so any approach that takes an incremental view of updating the logic behind whatever you're doing, in this case picking partitions, kind of benefits from approaches that totally retrain everything. And I think there's something interesting what you proposed about, or in a direction you proposed about incrementally kind of updating these things to respond to changes in the data. So really interesting kind of overall framework you have.
Right. I think updating, supporting changes is definitely very important for database applications and analytics, because yes, there are so many people who are writing so many different data, and even when I was doing this work, I also had some opportunity to look at some of the production data, right? And when I look at a query log, it does change over longer periods of time, over the month, right? The data volume for the same table can increase, the query might look different. So I think, over this longer period of time, there definitely does exist some shifts at various levels in the system. Yeah.
Cool. So I wanted to highlight one question that came in from the audience from Daniel, actually. So he's wondering, how much effort is it for database admins to implement your techniques? Okay,
yes. So for the first work, we actually the sketch part is we already implemented in a big data cluster. It's not that expensive because as again we use established lightweight sketches. So just pen a few other function calls when you ingest partitions, and they store some actual values. So that's for the stats part. And then for the modeling and clustering part, those are again in this case not XGBoost and simple Python scripts would work as a prototype if you don't care about getting the best latency. So having prototype implementation of this would, in my opinion, is not impossible in real database systems. At least you can get all the infrastructure you need to collect the information. And then for the second one, where you try to reorganize. So this is also so basically what we have is you can think of as a online learning framework or advisor on top of the current partitioning design. So what this I guess I imagine this to for example, it can provide specific advice to admins saying that okay, I think that things have changed. Maybe you should redesign your workload and again, the online algorithm that we use is pretty lightweight. It's requires you keeping count basically on high level, keeping counters of different options, and see how so implementing it is I would think is not a going to be hugely expensive. Whether they think it's worth it to implement to start with, I think is another question. And I will be, my hope is that I will talk to people and see if they're not willing to try something like this, what is the practical overhead and how can we change the design to make it more practical. Yeah.
think your evaluation is quite convincing, especially if they're already doing random.
Right. Yeah. So I think, yeah, it just depends on, some people are more open to trying, and also, for approximation, I mean, random also doesn't give you error guarantee. We also don't give you error guarantee, and some people are like not okay with that. So yeah, it just like people have like various levels of comfort with these techniques. But I think that's a really good question, and I think that how to come up with ideas that would be cheap to both give you the good results and also be practical to implement is very important. Yeah, and I think when we think about the automating for different type of data sets and more downstream tasks, I would also be curious to see what are other type of features that are similar to what we have for tabular data, and also lightweight, and that we can easily compute on large amounts of data and everything.
Very exciting stuff. We are technically 1 minute over, but I wanted to take a step back and ask a little bit of a higher level question. If you try to project forward, let's say 5 or 10 years, where do you think all this work about data analytics is going? What do you think the data analytics system of the future is? And what's kind of on the docket for you over the next few years as you continue working on this stuff?
Right. I think researchers have always tried to improve it, to make it faster, to make it more automatic, so that users can do the same thing with less manual input, and make it more user friendly, so that if you don't know much about specific libraries or tasks, you can still perform your task, right? So I think performance, usability, and like automation are all like great and exciting directions that we're moving towards and building towards, and also I guess supporting new kinds of workloads. So these two examples that I talk about are still on SQL queries, which a lot of people are still using, but a lot of other people are doing learning tasks or all other kinds of data science tasks. So yeah, I think there are a lot of open fronts and rooms for improvement, and it's not clear that there is like one thing that's more important than others, right? Like we kind of need a system to have all these aspects to keep working. So yeah, I think I'll be really curious to see that getting to learn that new challenges faced by users for new data types, type of analytics, data volume, and what is the best way we can do to improve them. So sorry, this is a pretty generic answer, but I just feel like it's not like one jarring problem that is bottom. I feel like everyone is bottlenecked, right? It's more like there are all these aspects of the system that we can always push forward, and yeah, and can pick one that's most interesting to you.
Cool. That's super exciting. So we're a little bit over the hour now. So I wanted to thank Kexin again for coming on and giving this talk. It was really great. Thanks everyone in the YouTube audience who came and attended. If you want to hear more about our our podcast or our seminar, you can go onto our website, mlsys.stanford.edu, and sign up for the mailing list. I think we send you at most 1 or 2 emails a week telling you, who's going to be on, a little reminder on Thursday morning. If you're on YouTube, subscribe to our channel, hit the bell icon to get notified when we go live. Next week, we have me on the podcast. So I'll be talking about some work on contrastive learning. So I hope everybody tunes in then, and we'll be very excited. So with that, we'll wave goodbye to YouTube and see everybody next week.